We're now going to begin our overview of the LockManager App case study. This is a new case study we haven't covered before, which is available at the link at the bottom of this slide. And we'll show how this case study can demonstrate how Spring WebMVC can be used to send and receive HTTP post requests synchronously to and from a microservice that provides a distributed semaphore capability. We've been talking up to this point about using HTTP GET requests, and now finally we're going to see how to use HTTP POST requests. And this will be interacting with a LockManager microservice. The client will synchronously acquire and release remotely managed locks, either individually or in bulk, using the declarative Lock API interface. This is also going to be different from what we've covered before because we're going to show how to use a special feature in Spring 6 called HTTP interface clients to generate proxies for us automatically rather than having to write them by hand. The LockManager application server is a microservice that acquires and releases locks either individually or in bulk. The LockManager controller, as usual, converts all the HTTP post requests it receives into standard or user-defined Java types and forwards them to the LockManager service. As you can see in the LockManager controller interface shown here below, we pass over standard types like integer and list, and we're going to also be able to pass back and pass over LockManager as well as lock. And we'll talk more about that as we go along. LockManager and lock are classes that we define. The LockManager service uses an ArrayBlockingQueue object and virtual threads to implement a distributed semaphore. We'll talk more about what ArrayBlockingQueue is in just a bit. It's a standard Java type that's used in order to be able to provide a bounded concurrent thread-safe queue. So let's talk about the structure of the LockManager application project. This project's source code, as usual, is organized into several packages, one for the client, one for the server. On the server side, there's a folder called Server that contains the app entry point, the controller, and the service implementation. I probably should have called this microservice instead of server, but it doesn't really matter for the purposes of this discussion. As we mentioned before, the implementation of the controller sends and receives a range of standard and user-defined Java types, such as lock and LockManager, shown here. In turn, the lock and LockManager classes are defined in the common package, which consolidates various project-specific helper classes. In addition to lock and LockManager, it also defines other classes for things like holding the constants, a nice callback interface, as well as the server beans that are used to do auto wiring and dependency injection for some of the capabilities we'll discuss later. There's also a utils folder, which contains general purpose utilities to do things like log output and generate unique IDs for the LockManagers. And then finally, there's a resources folder that defines various application properties like the name of the LockManager project and the port number where the server listens. There's also the client side, which is nested in the test portion of the package, and this includes the LockManager test, which is a test driver that initiates synchronous calls to the LockManager microservice. We use Java parallel streams in the LockManager test file in order to emulate multiple concurrent clients sending and receiving requests to the server to acquire and release the locks. There's a client folder that contains a couple of classes. One is used to send and receive HTTP post requests to the LockManager microservice synchronously. And we use post requests here because the server's state is being modified. All the various operations we have, like create and acquire and release, all update the state of the server. And if you take a look at the link at the bottom of the slide, that's the reason for using post requests as opposed to get requests, which are meant to be read-only. We also use this declarative HTTP interface feature that was defined in Spring 6 and beyond to support automated proxy generation. So we no longer have to write proxies by hand, which is wonderful. There's also a resources folder where we can enable or disable Spring logging by controlling the verbosity level of it. By default, it's rather verbose, and so we can turn off some of the verbosity to only get messages having to do with real errors. So let's talk a bit about the pros and the cons of this LockManager app case study. So some of the pros. As we'll see here shortly, we're going to use the deferred request mechanism provided by Spring to avoid blocking the so-called servlet thread. And this will allow us to improve system scalability in certain environments, either ones that use traditional Java threading, such as the ones before Java 19, or the ones that now use Java virtual threads. We'll get better control over this. By the way, the servlet thread is also commonly known as an HTTP worker thread. You'll hear those terms used somewhat interchangeably. I'll try to stick with HTTP worker thread as much as I can. There's also a very clever use of the ArrayBlockingQueue to avoid having to know anything about more detailed Java synchronizers, things like semaphores, for example. Now, it turns out if you want to learn about these synchronizers, I have plenty of videos out in my various Java playlists on YouTube that talk about Java synchronizers in great detail. But to try to keep this particular case study self-contained, I didn't want to require knowledge of things like how a Java semaphore worked. And then we also use this declarative Spring 6 HTTP interface mechanism to have synchronous proxies generated for us automatically. And again, this just cleans up some low-level, tedious, and error-prone manual programming that we've done in previous case studies. Of course, not everything is unicorns and rainbows, as I like to say. So it turns out, even though we use this deferred result class from Spring, the client actually isn't asynchronous. Only the server is asynchronous. So as a result, client threads can block when they're trying to acquire or release the locks, which can in fact cause timeout problems if the blocking takes place too long. And I'll actually show you how to get control over that by using some cool features that are part of the programming mechanism that's available with these modern web services in Spring WebMVC. Another issue here is that the server uses the Spring WebMVC thread pool model. And this pool defaults to a fixed number of traditional Java threads, these so-called HTTP worker threads, which are not virtual threads. So there's some issues there, and we're going to talk a bit about how to get around that. In particular, this design shown here for the LockManager app case study does not take full advantage of Java virtual threads. We'll address this issue in some upcoming case studies using other forms of Spring. And another problem here is that the ArrayBlockingQueue implementation is not an optimal way to implement a distributed semaphore. There are other ways that are more optimized, but I wanted to keep it simple for the purposes of this demonstration. We'll address some of these limitations later by using both WebFlux as well as Java virtual threads. But this is just something here to get your appetite whetted and to show off some really neat features with Spring WebMVC and some interesting features like deferred result. So that's the end of the walkthrough, the overview of the LockManager app case study.